Okay, we are moving on to finally talk about one of the foundational concepts in chemistry. The concept of the mole and how to calculate the amounts of chemicals that are used or produced in the reaction. This term, the mole, has nothing to do with the animal. Okay? Now, just change. The mole has nothing to do with an animal. It's a number. Okay? Now, it's a counting term. You know how we use terms like a decade for 10 years or a dozen eggs. So, it's vitally important to not trying to put more into the term mole than it actually is. Mole, again, is the number. Are we clear? Okay, it should be your mantra. Mole is the number. And it's an incredibly large number. So 1 mole is 6.02 multiplied by 10 to the power of 23. Okay? This is called Avogadro's number. I can give you an idea. I mean, it's really like, think about this. How many people are on Earth? How many people? 7 billion. So 7 and a change. So basically it's 7 multiplied by 10 to the power of 9. That's how many people are on Earth. So you can like take 1 billion Earths and it's still not going to be a mole people. The best example to give you a perception of how big the number is, how many this is this. Bless you. The Earth as a planet kind of formed 4.5 billion years ago. Imagine that at the moment when Earth was formed 4.5 billion years ago, 1 mole dollars was created. Mole of dollars. It doesn't matter. Mole is the number. So 6.02 multiplied by 10 to the power of 23 dollars. And then every second somebody was spending $1 million. Every second. That's a lot, even by American standards. Okay? By now, that somebody wouldn't spend even a half of that sum. So it's an enormous amount of something. Does that make sense? Do you understand that it's a number? So, we use mole to count atoms. So, say 1 mole of carbon refers to 1 mole of atoms of carbon. When we say 1 mole of sodium, that's 6.02 multiplied by 10 to the power of 23 atoms of sodium. Am I clear? We can apply it to molecules. We can say we have a mole of water. Sure thing. Means 6.02 10 to the power of 23 molecules of water. Does it make sense? Now, this is an equality, the conversion factor for moles to particles and particles to moles. We're clear? Now, the next idea, which sometimes for some reason becomes confusing. So when we write chemical formula, we use the subscripts, right? Like C9, H8, H2S. Does that make sense? What these subscripts mean is how many atoms of each individual element are in the particular molecule. So in this example, molecule of aspirin has 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. Does that make sense? Mm-hmm. So in order to kind of make another valuable example, yeah, that was smart. Okay, in the bottom. Can you see what I'm writing on the bottom of the screen? So in this molecule, in one molecule, how many carbon atoms there are? 6. Hydrogens? 5. Oxygens? 6. That's glucose, by the way. Okay. Glucose, yeah. Now, can the subscript be a fraction, like 5.2? No. No. Why? Why it cannot be a fraction? Not half of the element. We can't have half of the atom, right? Atom means atom, undivisible. We can't divide it. We're talking about chemistry. You know, it's not nuclear physics. So, of course, you know, some of you can be really, really, now understand please, I'm joking, but smart and annoying, go somewhere and find formulas like lithium 2.3, hydrogen 5.6 and shove it in my face and say, see, it can be fractions, those are not molecules. We're not going to talk about it. There are situations when you can see a formula and there are fractions. These aren't molecules, these are totally different things. In a formula of a molecule, subscripts cannot be fractions. They're only whole numbers. Does that make sense? Now, one atom is very, very light. Are we clear? Now, if you take 1 mole of atoms, that's a lot, right? They will have some very tangible weight, very tangible mass. Does that make sense? So we call it a molar mass. Molar mass is the mass of 1 mole of an element. So let me give you an example. For instance, how many atoms are in 1 mole of sodium? 6.02, 10 to the power of 23. Does that make sense? So these many atoms, all together, they have a mass of 22.99 grams. Does that make sense? How can you find it? Huh? Say again? The atomic mass, you just write atomic mass and put gram per mole. Does that make sense? So, do you have a periodic table somewhere close? It should be in the book. One of the pages. You have it in front of you? What's the atomic mass of sulfur? 32 point whatever. 32.07. Okay, good. So atomic mass is 32.07. Just it. The molar mass of sulfur will be 32.07 grams per mole. What the vitally important thing to understand here is the unit. Do you understand what grams per mole are? That expression, grams per mole, it means that, for instance, 32.07 grams is what this is the weight, the mass of 1 mole of sulfur. Does that make sense? We're clear? Yeah. Let's say it's 32 grams per mole. How many grams will 2 moles of sulfur weigh? 64. Half mole? 16. Does that make sense? This is like super important. Like I cannot even stress how important it is. Question? So this is the conversion factor. For instance, 1 mole of carbon is 12 grams. Well, 12.01. Okay. 1 mole of lithium is 6.941, basically, 7. Does that make sense? So we're going to be rounding molar mass to the 10th. Okay? Got it? Or at least 3 significant figures. So how do you calculate? First of all, before we move on, do you understand how to express, how to find a molar mass of an element? What's going to be the molar mass of copper? Which I totally don't remember. Huh? 65? 63.5. Yeah. 63.5. 63.5 of what? Oranges, apples? 63.5 grams per mole. Does that make sense? Units. So, how do you calculate a molar mass of a compound? Before we move on to this, like there are steps. Steps are fine. But let's talk about water, shall we? What's the formula of water? How many molecules are in 1 mole of water? Well, start with 6 and we assume that everything else is kind of obvious. 6.02 blah, 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 blah. You got it? All that number with 10 in the power of 20. Does that make sense? So there's you have 1 mole of water molecules. Now I'm going to ask you a very simple question. Don't overthink it. How many oxygen atoms are in 1 mole of water? Bingo. 1 mole. How many hydrogen atoms are in 1 mole of water? 2 moles. Because each molecule of oxygen, each molecule of oxygen contains 2 hydrogen atoms. Does that make sense? Go ahead, ask.
I don't want it to be a dumb question, but
No.
I was going to ask, like, so if we were to do hydrogen, will we do like 2 parentheses 6.02, or no, it'll all be one thing? I'm overthinking it.
I think you are. You're like, it's just, okay. Let me ask a different question. You have 1 mole of cars. Can you have 1 mole of cars? There's going to be a lot of cars, but you can have 1 mole of cars. Each car has 2 women and 1 man. How many men are in those cars? 1 mole.
1 mole of men.
How many women are in these cars? 2 moles. Does that make sense? Because there are 2 women per car. And then 1 mole of cars. Does that make sense? So, what I always tell you that chemistry is very visual science. You have to think of moles not as the number or term or anything. Like, imagine you have actual particles like floating around. Does that make sense? So, basically, next question. If you have 2 moles of hydrogen and 1 mole of oxygen, What is the molar mass of oxygen? 15.999, but since we rounded up, it's 16. Okay. What's the molar mass of hydrogen? 1. We need 3 significant figures, so 1.01. That makes sense? How many moles of hydrogen we have?
2.
So what's going to be the total mass coming from hydrogen? 2.02 grams, right? Because each mole was 1.01 gram, we have 2 moles, we have 2.02 grams, right?
Yeah.
How many is coming from oxygen? 16 grams. What's the molar mass of water? 18, well, 0.02. You got it. Does that make sense? So basically, take a molar mass of an element, multiply it by a subscript. Oh, it's not 16.1, it's just 16. Just 6, sorry, it's just 16, just 16. Okay? So, here's the thing. So I have CH4, okay? Does that make sense? What's the molar mass of carbon? 12. What's the molar mass of hydrogen? 1.01. What do you need to multiply molar mass for hydrogen by? 4. Does that make sense? Because we have 4 hydrogens. Are you following me? 12 plus 4.04 will give you 16.05 grams per mole of methane. Does that make sense? Well, how about we do that for glucose? Now, please, to make it faster, just round up to the whole number. Just molar mass of carbon. 12. So, what's the impact of carbon? 72. Well, you can say 12 times 6, it's 72. What's the impact of hydrogen? 12. And oxygen, what's the molar mass for oxygen? 16. So 16 times 6 is going to be 96. Okay? So put it all together, it gives you 170. Actually 180. 180. Does that make sense? You understand what I just did? So that's how you calculate the molar mass of a compound. Remember, that's going to be if I will tell you what's the answer, you should say 180 grams per mole. Not just grams, grams per mole. It's the molar mass. Am I clear?
Yes.
Now, okay. How to calculate moles from mass or mass from moles. So to do this,
we don't need to memorize all those atomic numbers.
oh shit, no.
Okay.
Are you kidding me? I've heard that, sometimes, and students are asked to do that. Oh crap, hold on a second. PowerPoint went out. So sometimes students are asked to memorize periodic table, which is like totally ridiculous. Okay. So I'm going to introduce a new slide. Okay, there we go. So let's do a practice thing. So I'm going to tell you something. I'm going to tell you that you have 50, oh crap, hold on. You have 29 grams of sodium chloride. how many moles of sodium chloride do you have? It wouldn't be that easy. So what do you need to calculate first? What's going to be the conversion factor? So if you need to go from grams to moles, what should be the conversion factor? It should be grams. You should multiply it by moles over grams. Does that make sense? So you need to find out how many grams 1 mole weighs. You need to find a molar mass and then flip it upside down. Does that make sense? It's as simple as it can be. So in the task like this, again, 29 grams of sodium chloride. What do you need? And the question is, how many moles? So my first question is, what you need to find first and foremost? You need to find molar mass. Let's find it out. What's the molar mass for sodium chloride? Sodium, I don't remember, 23? 23, and the molar mass for chloride, so 35.5. 35.5. So what's going to be the answer? 58.5 grams per mole. What does that even mean? That's a simple question. 58.5 grams per mole. In one. So the 1 mole of sodium chloride weighs 58.5 grams. Now, what do you need to do to find out how many moles are in 29 grams? Yeah, so 29 grams, 29 grams, let's say it's 9, divided over 58.5, right? Grams per mole will give you approximately 0.5 mole. Does that make sense? The whole approach. Quick and dirty. Whole numbers. No tenths, no hundredths. 72 grams of water. Grams of water. How many moles? No, 72. 72 grams of water.
4.
Perfect. 4 moles. Everybody understands how we got there. So, 72 grams of water. What's the molar mass? 18 grams per 1 mole. So, you divide 72 by 18, you get 4 moles. Does that make sense? Let's do the opposite one, which is super simple. What is the mass of 5 moles of glucose? What do you need to find first? The molar mass for glucose, which we had until PowerPoint gave up on me, but I can tell you its molar mass, 180. Molar mass is 180 grams per mole. So 900 grams. Does that make sense to you?
Yeah.
You got it?
Yeah.
So those are pretty straightforward calculations. Not for this unit though. Don't worry about it. Okay. Now, we're going to come back to these calculations when we'll be learning how to calculate the amount of chemicals used or produced in the chemical reactions. The chemical reaction is when one substance is changed into another chemically. So what it means is that in the very beginning of the chemical reaction, you have a certain number of atoms. Let's say you have a reaction between water and zinc. Okay? Which elements you're going to have in the products? Which elements only elements you can have in the products? Hydrogen, oxygen, and zinc. Perfect. No new elements are created, right? At the very end, I will show you the joke. It's like a very super nerdy joke about chemical reactions that we had in college. So that's important. Nothing new is created. And you have to understand that the number of atoms that you start with, the number of atoms that you end with are the same. No matter is created, no matter is destroyed. Okay? Does that make sense? So, I really like this statement. Reaction may be observed by the formation of bubbles, change in color, production of a solid, or heat that is produced or absorbed. Anyone is going into medical lab technology in the future? Smart choice. But if you would, there's a saying about all biochemistry and molecular biology. It's a science about looking at the minuscule amounts of colorless liquid. It doesn't change color, nothing happens. Like, you mix stuff, you look at this, nothing happens. It doesn't have to be bubbles, it doesn't have to be the color change. Many reactions, they happen without really anything being changed that's observable, easily observable. Does that make sense? Bless you. So, we kind of know that, so I'm not going to spend too much. When you write a reaction, things to remember. Reactants are always on the left, and always from the left to right. Products are always on the right. The arrow represents the direction. Okay? Reactants and products are separated by pluses. If you see a reaction with two arrows, what does that mean? It's reversible. It happens both ways, okay? Tricky question. What if one arrow much bigger than another? Yeah, so it favors to the right, in this case, the direct reaction rather than the reverse reaction. That make sense? Over the arrow, you draw the conditions. It can be temperature, it can be pressure, it can be catalyst, whatever is needed for the reaction. Does that make sense? The indexes S, L, G, or AQ, they explain what kind of physical state your reactants or products are in. So, for instance, in the reaction that I wrote here, water at the room temperature, it's liquid. Zinc at the room temperature, solid. And what's produced is, if you boil it hard enough, and so water will be, sorry, not waters, hydrogen, okay, which is going to be gas, and aqueous zinc OH. I just don't have space to write it down. So let me give you another example which will be clearer. So say solid zinc plus aqueous solution of hydrogen chloride, hydrochloric acid, will give you zinc chloride, the aqueous solution, and hydrogen gas. So in this parenthesis, you write down the conditions, the state of the reactant or the product. Does that make sense? I'm going to stop here if you want to see that nerdy. You know what the gravitational constant is? The G-force? So I had a joke how to produce hydrogen in the lab. You take mercury, heat it up really, really hard, and the mercury will decompose into hydrogen and 2 gravitational constants. I'm not expecting anyone to laugh. It wasn't funny even when we joked it. But that's an example of not a chemical reaction. You're not producing new element from the old element. Does that make sense?